Hey there, Vince here, and welcome to yet another Circuit Rewind. Today I want to talk a little bit about tools used behind the scene like what I used on the arcade cab recently. One of those tools is a multimeter, but there's another tool called an oscilloscope, which I haven't really pulled out and used on the channel yet, I don't think. I actually have two examples of them right here. So this right here is just an oscilloscope. It has a single probe on it, which I can go and clamp to a wire, and then has a ground return lead to complete the circuit, compared to one of these, which is actually a full multimeter. Well, what separates a multimeter from an oscilloscope? Many of you are probably already familiar with a multimeter. It can measure things like your voltage level, your resistance, capacitance, depending on the type. Some of them have diode meters and a few other things here and there. Some can do DC voltage, others do AC voltage or both. Like everything I just named, this does all of those. But what does an oscilloscope do? Well, it just measures voltage. It doesn't do any of that other fancy stuff. So if we have multimeters, why would we get an oscilloscope? What is the actual difference? Well, it turns out that an oscilloscope doesn't just measure voltage, it measures voltage over time. That's sometimes a lot more valuable than any other measurement you can take, because time is a very critical thing when measuring components. The thing is, these are both very cheap oscilloscopes. So yeah, this multimeter, it has a full digital display that can show the waveform and everything, just like this little mini one does, but that's not what I'm here to talk about today. As I'm developing newer custom PCBs, like the one for the arcade cabins and the ones used in the Windows 98 retro rig, which you haven't seen yet, but I'll have some videos on soon. I've decided I need some better diagnostic hardware for my lab here. This just arrived. Let's get this thing open. And what do we have inside of this box? Come on. A box! Holy crap. All right, let's get that one aside. So we have another box. The difference with this box is that it says Rigel on the tape. So let's get this open. As I expected. What's inside the box, do you wonder? Another box. I love modern shipping so much. And yes, it's upside down right now. I will correct that. Fancy. So you saw like the little oscilloscopes. This is their big brother. Like this thing, this is a chonker. I like it already. And more importantly, we have power adapter, some wire of some kind. That looks like it's probably the USB cable, which will be handy. The other part of the power cable, so that's the high voltage side versus this was just the brick. Let's see, probe, 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 and probe, because this has 4 probes on it instead of 1. That's actually one of the biggest reasons I wanted this, is so I can compare multiple values simultaneously, all on the same device. Anyway, with that, I'm going to get this thing plugged in because I have actually a test circuit already set up sitting right next to me that you didn't see yet. Oh! So I just realized, and I should have realized this sooner because I did look at the product spec significantly before I purchased this. This power brick is just standard USB-C. But what's nice about it, it is a custom USB-C plug. Whereas you can use a normal one, and God, this twist tie is on here in a weird way. Anyway, a normal USB-C will work. I will check the voltage and amperage here in a second. This produces 20 volts at 3.25 amps. 12 volts at 3 amps, 15 volts at 3 amps. I'm guessing that higher one is probably what this is. It's a 65 watt adapter, but there's a little peg right here. That way when you stick it in, it kind of locks into place. Oh, that thing's not coming out, which is nice because eventually I do plan on having this thing be quite mobile. One nice feature is that this is a VESA mount on the back of it. So I'm going to get a monitor arm over in my main electronic soldering station area and actually have this mounted to the wall so I can just grab it and move it around, and then I can just push it out of the way or bring it down. That way it's not actually using any of my desk space. But that's a project for much later because I need to build the wall mount that the monitor mount would plug into. Are these? Oh. Ooh. Tilty feet. I like that already. Hey, did you know that this is actually a power strip that I'm sitting at? I mounted a power strip to this desk. Maybe someday I'll show you that. That way I just have power right here. And this thing should be doing something, maybe? The light has RGBs, it looks like. So if I press that, I see RGBs all over the place. Do I get a screen? I do. Oh, hey, look at that. I have a little bit of a screen. Oh, this thing has a fan. I can actually feel air pressure on the back of it. From other research I've seen online, if I'm not mistaken, funny enough, this thing's actually just running Android. So it's booting Android, which under that hood is just Linux. So apparently this is just an Android app on a very fancy tablet, but it doesn't matter too much. An OS is an OS, right? What matters is all the accompanying hardware that's plugged into that the OS is being able to feed from and pull that data from. And because it is Android, that means there's a lot of extra features that this thing can do that traditionally just would be too cumbersome to actually implement into a device. So now that that's hooked up, I'm going to go grab something else to make this easier for both of us at the same time. So I cleaned up the area and brought out some extra toys. I've got the oscilloscope here, and I've got one of the probes ready to go. So this is just a nice BNC connector. It should just slot right in. And everything is default on this right now. I've not changed any settings. I've not gone through menus or any of that stuff. So this is all new to me. So what's really cool is one of the reasons I wanted this specific scope is notice how I can just record the screen straight off of it. This has an HDMI output, but that's not actually what I'm using right now. This is actually transferring the video feed over the network to my laptop in real time. What's really nice about that is that it's actually a bidirectional interface. So this oscilloscope has a touch screen, but I can touch the screen with my laptop. So I can just go here and start navigating things. And hey, look, like here's the menu interface, right? Which I haven't even gone through this yet other than just plugging in and to get the IP address. What's really cool is that, like I said, with this being a normal operating system like Android, it supports a windowing system. But what I've got for you now is I've got this little thing. This is an ATtiny85 based microcontroller, and straight from the factory it ships with the default Arduino Blink code on it. So it just has an LED blinking on and off. That's it. And I want to look at this with the oscilloscope. So first things first is we need a complete circuit on the scope. The grounding alligator clip on the probe, I'm just going to attach straight to the outer jacket of the USB connector there. And then with the probe, it has this little hook that I should just be able to come in and put it right on the pin. And just like that, our line is there and it disappears. So the next thing I need to do is start figuring out the voltages on this. I remember that now from watching other videos. There's actually a voltage divider directly on the probe that I needed to flip. So it's doing a 10-to-1 divide of the value. Look at that, it's right where I want it to be now. So this is what I find really, really interesting here, is that Arduino code is up on the screen now. It's literally just digital write high, digital write low. And you'd think of binary as just this square waveform, right? And that's what we're used to working with when working with computers. But digital devices exist in an analog world. And so in the analog world at a high enough frequency, you are still dealing with something like this. So as you can see, when there's the trigger from the 0 state to the 1 state, there's actually a subtle dip before it rises. It actually overshoots and then comes back, and you can actually see that full curve of the transition from the 0 state to the 1 state before it flatlines out again. And that's really why I wanted this. One of the reasons I wanted this is I can do deep dives into signal timing. Because when you're dealing with a clock, you may have a clock and a bus, so the clock is just going, high, low, high, low, high, low at a certain frequency, and there's a timing between when that clock pulses high and low and when the actual bits of data on that bus are 1 or 0, and there's going to be a bit of an offset on it. So the clock goes high, for instance, that's called the rising edge. Like as we can see here, this is a rising edge signal. When that happens, it sends off a chain reaction delay, but as you can see, the actual high signal is slightly later than when the actual code told it to do the thing, right? I'm explaining this terribly, but basically there's a slight delay between each of the signals on a system based on the clock and the actual data being transmitted. And sometimes, like when the chips actually do the sampling of MIO1 or MIO0, maybe too early or too late. And so, as you can see here, if it measured it like right here when it first detected it, it may be kind of in this middle state and could be flapping back and forth between a 1 and a 0. That's called basically a floating state when you're in kind of the gray area. Like let's say, for instance, on a 5-volt circuit, if you're below 2 volts, you're a 0. If you're above 3.5 volts, you're a 1, and then there's that middle area where it can't quite figure it out. Those numbers are just made up because every chip handles that differently, but that's basically kind of how digital electronics work. At least, TTL electronic. There's obviously different types of signaling besides just this voltage level signaling. There's radio frequency signaling, there's differential signaling, there is I guess I was going to say the PCI Express bus, but that's multiple differential signals. Your USB bus is a differential signal, so there's different ways of doing this, but at least all the stuff I'm working on, just voltage levels. And that's why I wanted to be able to record a voltage level at an extremely high frequency so we can see things like this. So now I'm going to set this back to run, and I'm going to set the, let's see if I can do trigger, and I'm going to switch the trigger to the falling edge instead. And now I'm going to press the button. And as you can see on the opposite side, when we transition from a 1 to a 0, you can see that it actually droops down too far and then kind of comes back up to a flat line signal. So kind of the same thing, but we can also see that it's not instantaneous. But anyway, that's what I wanted to show today. The reason I wanted all of this, I will show you here in a second. All right, so the first thing I actually want to use this thing legitimately for is I recently picked up this Netgear network switch. Or actually, it's not a switch, it's a hub. Yes, this predates switches. This is only a 10 megabit hub. So it has 16 ports on it, plus 2 on the back. And it's this port on the back that I'm most concerned about. This BNC connector is 10 base 2. It's what we had before RJ45 for Ethernet, if you could believe it or not. So what I'm going to do is I'm actually going to try to unplug this BNC connector here. Because 10 base 2 is also BNC based, I want to see if I can just plug this thing straight in and what kind of signal I can get out of it. Because right now it's not working. And I want to debug what's going on with this. I see nothing, which is basically what I was getting when I plug it into the network. There's no activity whatsoever. But like I said, there's 2 ports on the back of this, right? The other one is an AUI to BNC connector. And that thing does work. So when I plug this in, everything lights up immediately and I get a signal. So let's see if this thing shows anything. Now, I'm not sure what a 10 base 2 signal is supposed to look like here. Yeah, we can actually see some of the signal coming in and out of this thing right now. Because that's the thing, like this is plugged into my main network and there are a constant amount of broadcast packets. Let's say an ARP request that converts an IP address to a MAC address, that's a broadcast packet. A DHCP packet, that's another type of broadcast packet because you don't have an IP address and you're trying to acquire one. And there's other broadcast stuff going on for like device discovery and device communication. There's a lot of stuff on this network. Like if you can see the transmit light here, it's just constantly blinking. Anyway, this is really cool because I can see that there's traffic. I can monitor traffic. I don't care what the actual bits are. But now I can open up this device and start poking around inside to figure out where that signal is. And using the other probe, I can actually start probing pins within different chips to see where that signal is missing. Whether it's like a broken solder joint, like a cracked solder joint, or if there's an actual faulty chip or something inside, I will now have the tool to go and debug this thing. This thing can pick up, it's picking up the signal just fine. It's more than fast enough to see the waveform of the 10 megabit signal, which is awesome. And I figured this would, considering this can see up to 250 megahertz. So 250 cycles per second versus 10, you know, that's kind of faster. Anyway, I'm not actually going to do the deep dive of the debugging of this tonight. I just wanted to get this out to show that I have an oscilloscope now and a basic idea of what they can do. And I'm going to learn this thing because you saw me unpack it. This is my first time using it, and it does a hell of a lot more than my little handheld ones do. So I want to learn this thing more, and then I'll have, this will probably be a staple in the video as I do custom circuit boards in the future and diagnosing hardware in the future. But until next time, I'm Vince, this is Circuit Rewind, and take care, y'all.